So, without further ado, welcome Vignesh. Today we're gonna have Vignesh from the Developer Center of Advanced Laser Application in Munich. He studied both physics and electronics, and he gained a solid knowledge of hardware. His main goal is to make scientific data acquisition easy for the whole Python community, and he's gonna also be in the next event in the bot week and to meet us and talk about the web of things altogether. So without further ado, Vignesh, the floor is yours.
So I think what I can best offer today is a perspective into what we do in data acquisition in physics or science in general, and how we do this with Python and how we can have web of things in this. So already you know a little bit about me. So something about CALA, or Center for Advanced Laser Applications. So CALA is a petawatt peak power laser, which means laser facility. It's a R&D facility at the University of Munich. It's in Garching, Germany. What they do is they focus very intense laser pulses into thin targets and they generate ions from it. So this is what is ion acceleration, or laser-driven ion acceleration. For this, they have many different types of lasers and different targets, different diagnostics, which they want to measure the parameters of the lasers. So you have ions, electrons. You want to measure the physical quantities, and this is why they do data acquisition. And especially in CALA, everything is remote because, or most things are remote because either the laser is too strong or radiation is produced. So you can't be there where the experiment is happening. You have to sit in some other place. So that's why we do remote control, and when you do remote control, you can do it. You can bring the Web of Things standards in it. So data acquisition, you have, say, a light pulse. You can measure the energy of this pulse, or you can measure the cross section of this pulse. Yeah, can you see my mouse?
Yes, we can.
You can?
Yes, but yeah, the laser works too.
Yeah, so you can see the, say, cross section of this pulse. I can show you some today. And you can measure the duration roughly or even accurately if you want. So the question is, what physicists try to do is they do this different diagnostics and they try to stitch together the data to make some meaningful physical quantity. And when you say, for example, just this laser beam cross section, if you know the energy of the beam and if you know the width of the beam, which you can compute by measuring with the camera, and if you have a calibrated camera, you can tell how wide the beam is. And if you know how long the beam is, you can tell what is the energy per unit area, for example. And they do that. So you have data acquisition, then data analysis, then from that they extract the physics, then they do again the experiment, again they do data acquisition, then they do the data analysis. So it's a sort of a cycle as well. So this is why we do our data acquisition in a custom implemented way. And if you the way to write this is like any IoT device. It's called data acquisition, but it's actually just IoT stated in a different way, only because, as I said, data acquisition follows data analysis. From data analysis, you get physics, but what data acquisition is just IoT. So, or remote controlled, you just capture the data remotely. So for each device you have, you can make a thing implementation for it. And if you have a thing implementation, of course, with Web of Things, you get the thing description. So the device or the hardware or the server serving the hardware, it can push the data to data storage. This is one part of our software. One is GUIs in control room or anywhere in a control center within a lab. So this is where I use a lot of Web of Things or thing description itself, because I know web development, or I like to do web development for hardware. So then you can also use, you have scripting clients, computational post-processing, all this. They access our different hardware to achieve their goals. So a little bit before showing the hardware, and showing you what we have implemented today. So we use what is called as ultrafast lasers. So ultrafast lasers, they are, if you see the laser characteristics, they are very short pulses. So femtosecond or picosecond of that order. So 1 second is like 32 million years for a femtosecond. So, and the pulses per second, the laser I show you today is 10 hertz, but it can be many millions of hertz. Or if it's of the order of millions of hertz, it's called an ultrafast laser. But for high power laser, we usually do 1 hertz, 10 hertz, or somewhere in that range. You can do 5 hertz and even less than 1 hertz if you want. So this is pulse frequency. How many pulses you get per second? They have many applications like atomic clocks, spectroscopy. So for high power lasers, which what we have here. So how do you get a high power laser from ultrafast laser? So say you have a laser source, so it's giving some pulse lasers. So it will have some low energy and it will have a short pulse width in time. So you can just stretch the pulse, and then you get a low energy pulse, and you have a longer pulse in time. So this can be in nanoseconds or microsecond range. I don't know exactly how long it is, but you can stretch it. Then you do the pulse frequency reduction. So to do high power, you can't amplify every single. If you get 80 megahertz pulse frequency count, you can't amplify every single pulse in it. You have to cut the pulse frequency, especially if you're going to terawatts or petawatts, for example. So we cut the pulse frequency to 10 hertz, 1 hertz, or whatever hertz we want. Then we amplify it. Then we do the amplification is where you get a high energy but a long pulse. But after that, you can compress it to a short pulse. So this is the rough sketch of a high power laser. And as I said, we have many diagnostics just to like track each part of this section, because it's all custom built to our application. There is no like one, you can't like buy the whole thing from some, maybe there's some company that gives it, but usually people buy different components. They just buy sort of amplifier, they buy either the laser itself, and they just try to like modular, they try to put it together in a modularized fashion. So I would like to quickly show what we have. Again, this is, let me just go to, this is the other GUI, one sec. So I hope you can see something. This is our so the oscillator is somewhere behind here, or the laser source itself, and it comes to this part, and this part of the setup is called a stretcher. So the stretcher stretches the pulse. As I said, you get a low energy short pulse. You can elongate it with this, and to we again, you can see our monitoring diagnostics. For example, there's a camera here. There's one more camera here, and there is a pinhole somewhere over there. These are all meant for alignment and checking what's on the, what you see. So the stretcher, this is, hope that's okay. There's no, one sec. There is something. So you can, this is the pulse that you see, I think, with this camera here. Can you see my mouse yet?
Yes, we can see everything and the mouse and all the cameras.
So then after we stretch the pulse, today we are ending it somewhere before the amplifier, because it gets very bright. I can actually turn on the laser itself. So I think you can see some laser. So this is partly amplified from the main oscillator itself, and it goes to the stretcher, and it ends before the even higher. There are many layers of many what to say, there are many levels of amplification. So we stopped it with the first amplification. So here we are measuring, there is again a camera over there, and there is a, you can see this this is a fiber that is measuring the spectrum of the laser itself. And when it's here, actually, we have put an energy meter somewhere over. It's the energy meter is the laser itself. So this is what our setup is, at least what we can show today. And if you see so for each device, as I said, we have this is written in node-wot, or this it's fully powered by the thing description, and node-wot creates the HTTPS client. So if you measure the spectrum, this is the spectrum you can see, and this is the energy. So it's 8.5 millijoule per pulse. So usually it is, if you have 8.5 millijoules per pulse, you're already when you compress the whole pulse, you will be close to terawatts, or of the order of terawatts of power, or really close to it. It's above gigawatts, but just not terawatts. So to set up these kind of GUIs is, for example, say one application why you might want to use the thing description is, say, for example, I want to generate this input field. So I can just parse the property definition of this integration time, and I can say that if I can read the property, then I can give a refresh symbol. If I can write the property, I can just create this icon, and I can also observe this property, which means if the value changes somewhere else, then I can update this value here. So you can just parse the property description itself, and you can just auto create this GUI element. So that's where I use mostly the thing description standards and node-wot. So again, little about, let me just turn off the laser, one sec. So just coding implementation perspective again. So each device has properties, actions, and events. So properties can be like, if you have an oscilloscope, that can be time resolution, time interval, and so on. Resolution is how fast you want to measure. So it's like the individual. It's like ADC sampling frequency. So and time interval is how long you want to measure. So these are examples of properties, and actions are like start measurement, stop measurement, and events can be like, okay, after the measurement has finished, just push the event to the client. Just tell the client that the measurement is ready, so the client can just fetch the data. So what you saw in the previous GUI, it largely works exactly like this. So most of the say, one sec, sorry. So most of the data which I'm plotting is through events. Even this is actually the pulse count here you see, and again the spectrum you can actually see, even hopefully some, okay, there's nothing here. Yeah, actually the camera is streaming, but there's no change that you don't see anything. So but once the measurement or any data is ready, it informs the client. The client just fetches the image, or fetches the spectrum, fetches the energy, whatever is required to be fetched to be shown in a GUI. So finally, apart from the properties, actions, and events, I also use sometimes a state machine. So a state machine is supposed to say that, say if you're capturing a video, don't allow to change the exposure time. So if you're, or for example, if you're already running a measurement, you don't let the measurement to be started again. So this is the purpose of state machine. So we have so many different devices from different manufacturers. So it's hard to guess like what is the how they exactly work. So for example, we have 4 different types of cameras in our institute. So only one camera allows changing trigger value when you're running the measurement. Every other camera, you have to stop the measurement change the trigger value, then start again. So if you want to tell the user, okay, don't change the trigger value, then the best case, or you can implement a state machine to control this. So and finally, all these things have to be written in such a way that physicists can understand, students can understand, PhD students, they should be able to write these devices if they want. Uh, we keep changing a lot our experiment based on what we did before. So then they should be able to read the code and understand and know how to develop this further. So for this, it has to be easy. So we do it in Python, and we do mostly object-oriented design for this, and which means each of the properties, actions, and events, uh, they become different aspects of uh, the object-oriented, the class. So for example, if you have properties, how we can write this is, say, you just create the camera class. So you can write a get and set function. So within the get and set function, you can write the hardware side of the thing. So the hardware protocol, or it can be Modbus, or it can be any device, any manufacturer given hardware protocol. We don't always use Modbus or any standard industrial protocol, but our devices many times have their own protocol on the hardware side. So how the data is sent to the hardware. So that you can write in this get and set functions, and you can just encapsulate this in what is called as a descriptor. So this descriptor is a special Python construct. It has a get, set, and delete function automatically taken care for you. So you can just instantiate the object, and you can access the property using the dot operator. So same thing on the if you read and write to the client, so you can on the server, you can instruct your server to do this operation. And as far as the protocol mapping is concerned, so the getter will be invoked. Say you have HTTP protocol, so the getter will be invoked for HTTP get method. The setter will be invoked for put method, and deleter will be invoked for delete method. I think of course, in Web of Things or thing description, the delete is not a part of the standard yet, but it's possible if you want. Mostly, I also don't use it. So from this, you can go to the thing description. You can auto-generate it from the descriptor, or from this type of object. So say you can set the property to be observable. You can tell the the end user to supply the unit bounds and so on. You can just auto generate this for them, so that they don't have to sit and fully understand what the thing description is. They just get the thing description, and again you can give it to a client, and the client will just consume the thing description and give a client for them. So the standard is in the back, or it supports the standard drives the whole thing, but they don't have to know they don't have to fully understand what it means. So this is why that's where what I am aiming for, because these things students can also understand. They don't have to learn everything upfront. So similarly for actions, just actions map to object methods. So you can write action. You can even have an input schema for an action and output schema if you want. And within the action, you have to write the device driver code. So here I have snap function. So if the user says blocking snap, or if they ask in the GUI that give a blocking snap, because it finishes very quickly, so you can just run a snap function. It just fetches the image, or you can just make it asynchronous, or make it run in the background. So it's all possible. So again, from the action, so this is from the action decorator, you can again generate the action description. So I don't want to go further into it, because I think it's obvious, and of course the protocol will be the post HTTP method. And finally, for the events, again it's a descriptor, but it returns a pub/sub object, which is based on you can do pub/sub, or people say you can use some reactive frameworks where a callback is run whenever you change a value. So I use pub/sub, which means this pops up, you can just push an event or publish an event. So all the subscribers of the event, they can just subscribe to the event. So here I have not shown the data schema for the event, but technically you have to specify it. So finally, a state machine. It's just an object which takes, you have to specify what initial states you want and what is the start, what initial state it is and what states you want. And in each state, you can specify what action it is that you want to execute, or what property it is that you want to write. Here, property is not there in this example, but you can specify that. So then the state machine will take care that before executing, the state is checked. If the device is only in the set state, for example, if the device is only in the on state, I can run start video. If the device is in on state, I can snap. But if the device is in disconnected state, I can't snap an image because there is no camera to snap. So you can set the state machine state simply by calling set state. So for example, snap, before you snap, just set the state to capture state. And after you snap an image, you can set the state back to on state. So this is every single device which I showed you today, right from all the cams, from spectrometer, to the energy meter. It's all implemented like this. So even actually this GUI is in the, one sec. So this GUI is in the slightly old control system, but technically every single aspect of whatever you want to measure, you can capture it, at least in the devices which we use, you can capture it as an object with different interactions as different parts of the object. For example, I can change. This is a property. This is implement. I'm changing the frames per second. So it got synchronized with the laser frequency. That's why you don't see anything changing. Maybe I just put it to 7. So this is just it's made with the property descriptor, and these are all this above. What to say? These are all actions. I can start a position, stop a position, and same thing with also the web GUI I have as well. So it's still working in this. So same thing. So you can start, stop. These are properties. Again, I think I conveyed the point I want to convey. So especially with our laser, there is one important thing. The question is how we want to stitch the data. Say we have an energy meter, we have a camera, we have a spectrum or spectrometer. We want to know how we stitch the data for different from different devices for the same pulse. So how this works is, since we are right now running the laser at 10 Hertz, as you might have seen. So there is a hardware trigger that comes before each pulse. So when this hardware, the first hardware trigger comes, then the pulse comes just a short period after that. So, and with this hardware trigger, you can actually trigger each device. And some devices can be simply optically triggered. So they don't need a hardware trigger, but they can be optically triggered. And why this hardware trigger is needed is because you can synchronize the measurement. Say the rising edge. So at this rising edge, you can start the measurement of the camera. So the pulse would have passed because the pulse is very, very short. Then at the end, say you have a 5 millisecond exposure time. So you got exactly the pulse and not any garbage data. And if you don't synchronize with the hardware trigger, you can already see once it happened that when I kept 5 FPS, it's trying to, you couldn't see it refreshing in the screen. So these types of issues occur if you don't synchronize with the trigger. So that's why we do this triggered-based reading. And to do this trigger-based reading, each hardware trigger means that a pulse has arrived. So you can count the number of pulses by how many hardware triggers are arriving, and you can just distribute this hardware trigger as a software event within the system. So say again, energy meter, camera, spectrometer, each have their own things, their own servers, but you can just distribute, say you have a trigger reader. So what this is, this Arduino is, say, a trigger reader. So at every rising edge, it will give a software event which says what the short number is and what the short time is. Short means laser short. So the laser has just arrived. So one single pulse is called a short. So you can assign a timestamp, you can assign a number to it. So you can, for example, see it. Say, where was, one sec, other PC. So we actually have two computers, which is why I'm little not able to figure out where it's running where. So let's run it at 10. 10 is not also not good enough. So so you can hopefully see it's running. It is actually running at 10 hertz. So this is supposed to count. Let me just refresh it. Sometimes the event is not. So this trigger reader, we have an option to count the shots, and it just updates how many shots have arrived. We go to the other computer where it's already running. So actually, I already kept it running. It's already in readout state. So if I turn it off, I have idle state where there is the trigger is not reading out anything. So if you go to readout state, I can already see today I had like 38,000 hardware triggers, and for these many triggers, I can have pulses. So you can assign based on this trigger one pulse number and one number and time to each pulse. So from that, you can assign to each energy value or spectrum value what is the pulse number and the pulse time. So that you can do by propagating this whatever this short number and short time from the trigger reader to each of the devices. So they will just catch this event since they're also triggered along with the same trigger. So they can just assign the timestamp and number to that value. Say it measured 1.7 milliwatt. Say it can just say that for short number 3000 taken at 4 p.m. 1.7 milliwatt was the energy, and this is the image, for example. So in this way, irrespective of whether you're running the, you can see our setup is somewhat distributed. We have diagnostics running. We have a camera here, we have a camera here, we have some energy meter there, but we have the spectrometer here. So the question is, the pulse is traveling all through the entire setup. So the stretcher, despite wherever the data is coming from, we should be able to correlate the data, and that happens by assigning the short number and the short time by using the trigger event as a reference event for the short number and short time. So I really can't show it today, but I hope if you see some energy data, what we measure, say that whatever I showed you in the GUI, if you store it to a database or to a file, what it might look like is I have a short time, right? And then I have a short number, and I have a value of the energy. So this is not from today; it's from like 6 months back at least, I think. So, but this is for each device. We actually get the same short number and short time for each measurement. So we know, okay, this camera belongs to this energy, or this camera image belongs to this energy, or this spectrum belongs to this energy, for example. So this is a specific this type of data acquisition is specific to pulse lasers. So that's why I wanted to mention about this. And finally, one thing I want to say is about how to synchronize GUIs. So we have, you might have seen, we have different GUIs. For example, one is running in PyQt. Actually, I'm using this because it's a very scientific GUI. I can draw some markers. Actually, maybe let me just set some value. Or there is already one running with a marker. So so this is already updating some frames. So this is the actual laser pulse you can see. So I can draw some marker like this. And this is a very scientific, or what to say, we made this GUI for scientific reasons, because I'm fetching the raw image, which means this is probably a 12-bit image, not 8-bit. So you can't, we're not making it to JPEG. So if you use a JPEG, you have to compress it. So maybe, so actually, yeah, sorry, this is actually a live image. You can't see it updating because it's supposed to be almost as static as possible. But this we are streaming with JPEG. But usually for some scientific applications, you need something a little more robust than a JPEG, which in JPEG, because in JPEG you lose data. And we have some features like you can change the maximum, you can normalize the image value, max value. You can even let the image auto normalize it. And you can show the axis, how many pixels are there. And you can draw some crosshair. I don't think this will come because it's somewhere else. Actually, it's too big. The pixel sizes or the image frame size is somewhat big. So you can see in what pixel values this particular image or particular laser beam is being displayed. So why we do that is they align the laser every day. So you have to pass the laser through the entire setup, which means for each camera, we show some alignment marks, which are stored like this. They're either within the camera or somewhere. You can just even store it in a file if you want. So, and we place the camera marks and they adjust the optics to make sure that, so each optics has some screws. You see small mirrors and you see all these mirrors. These are all optics which you can just adjust to change the pointing of this beam. So I don't want to do it now, but that's how you, what they do is before they amplify to the high power, so say whatever this millijoule, but again, the power itself is already in many gigawatts or close to a terawatts. So before you do that, you might want to align your entire laser, then you want to amplify. So that's why this type of, we use this type of special previews apart from also web previews. So we want to synchronize these GUIs despite where they are running. So again, that was my first point why I started with this. So say user start measurement from one PC. So another user or same user, if he's using a different computer, he can really stop the measurement. So you can again use a state machine for this. As I said, you're in on state, start acquisition, go to an acquisition state. And if you stop the acquisition, go back to an on state. And if some fault happened, for example, if one of this camera was running at 50 FPS today and we were skipping many frames. So this type of faults happen whenever we actually, when we apply some wrong settings, or even that, the camera is just misbehaving. That can also happen because we are using, especially when there is ionizing radiation, so it disturbs electronics, and the electronics don't like this and they stop responding. So that's when you can use a fault state to to keep a reference that you cannot turn back acquisition again. So if it's in fault state, you only have to reset fault and go back to on state, or you have to go and unplug the camera and put it back, for example. And finally, you may have enable disable state, which says you can use or cannot use the camera because of some reasons. Maybe it's dangerous to use the camera. It's too much energy. Actually, all of these cameras we have, they are heavily filtered. Some of these cameras are not, but some of them are very heavily filtered. You can't see anything without putting the filter. So you can use a disable state for this. Just for example, many things I say now is like some argument's sake kind of. It's for argument's sake. So it can mean it can be something else also as well. So when you have the state machine, you can instruct you can use this state machine to tell the user or a GUI how to show the screen, how to like paint the current preview. So when you say start measurement, someone say this is a preview for the spectrometer I have. So someone clicked on start measurement, then they can only click on stop measurement. So that means what you can do is you can promote the state machine state to a property, and you can make the property observable, which means whenever say you went to acquisition state, send a change event to all the clients that, okay, I have changed my state. And you get this automatically if you have an observable property. And same thing with stop measurement. Whenever you change, whenever you should stop measurement, issue a change event to all the clients. Okay, I went back to on state. So then you can tell, you can inform the GUI, say GUI components. So this is a button. So you can tell in on state, okay, say the stop button. In on state, this button should be disabled because it's an on state. It's not in measuring state. So or if it's in measuring state, it should be enabled. So disable is false. So similarly, say this disconnect PC and hardware. If I'm in measuring state, then I just disable this button altogether. So text is some dot dot dot, and actually the button should also be disabled. And you don't even display anything here so that they don't know what it is. And if it's in on state, you can disconnect the hardware, and if it's in disconnected state, you can connect the hardware. So if you use especially React or some other reactive framework like Svelte also, you can do this in context API or there's a use context hook, which you can supply the state property in this context hook or context value, and you can propagate this value down through all the elements or all the GUI elements. So and finally, if you with the use, there's a use effect hook also. It's just when a value changes, it repaints the screen. So you can just apply the state itself to the use effect hook, and it will repaint the screen. So for example, say maybe I have this. This is not this computer. Sorry. Let's show 9. Yeah. Let me see if I have the other GUI. So yeah, it is running. So you are capturing the spectrum. So this is actually the same image, is just wrongly calibrated. That's why it's looking different, but it's actually the same. So you can, let's say this GUI is in some computer one, this is in some smartphone, and this is in some other computer. So I'm saying now that the state is measuring. So when I say stop, so it went to it set the state machine state to on, and you can see the state machine state I've printed on this table also. And it stopped here also, and you see this button here again. I can control the acquisition again with this button. It's an action. So sorry, you just go back. So if I click start here, it goes back to stop. So if I click stop here, it goes back to start. So that because it knows what is the state, and it's receiving the state as a change event, and it's just repainting whatever this button means, and it's also changing the action to be called. So I start here, so I can stop here. So that's why I didn't want to show it this. But you can see it went back to on state. So not only I'm changing the text, I'm changing what action to call, and I'm changing the okay, here I'm not, in this case I'm changing the text disabled, enabled, or the text color also. So this is one way you can synchronize GUIs irrespective of wherever this thing is, wherever your things are running or wherever your previews are running. So every single preview I run here is actually like this. Even the cameras, actually it doesn't even matter what it doesn't even actually matter which protocol you use because the properties, actions, events, they're independent of protocol. In Web of Things protocol, so each property can be written with its own protocol binding, irrespective of the protocol implementation itself. So I can do, so this GUI is actually written in ZMQ. It's my own client. It's almost identical to the node-wot client, but in Python. So just the protocol implementation is slightly right now diverging from the standard, but someday I will try to merge it with what's already available in the standard. So anyway, so say this is overview region camera. So this camera is in capture state. So actually, let me choose some other camera. So this camera is in capture state, and this is a button. Sorry, not this. Let me just quickly go back. Stretcher guitar. Okay, stretcher guitar. So I think this is a very, this image and this image is actually the same. It's just, it's very far away. So now you can see it's actually one and the same. So if I press stop here, so if I press stop here, it goes. You can already see it has changed here, and I can start here, and it'll already go to capture state here as well. So you can see it's working correctly, or you can see it has changed correctly. So that's how you can use state machines to coordinate your GUI elements or what you want to show to the user. I think that's all I have for today. If you have any questions, you can ask me. I hope my audio was clear. And special thanks to Professor York. He's the chap for this experimental physics, whatever laser you saw now. And he allowed me to use the laser for this demonstration. And Anna, as you know, she co-organized the whole laser side of the thing. So this is some icons, some attribution I used today. So any questions?